Okay, hello everyone. Again, my name is Gary Forman. I'm from the Department of Astronomy, and today I'll tell you a little bit about my work in modeling the most energetic light from our neighboring galaxy. So first, let me get you oriented with the picture I have plotted here. This is real data from the Fermi Gamma Ray Space Telescope, which has been performing an all-sky survey for the last about 4.5 years. And to give you a sense of how large this image on the sky is, this white streak here is 1 degree. That's about twice the size of the full moon. So we have a pretty big coverage in the night sky with this image. And so the first part of my title was the most energetic light, and by that I mean gamma rays. So gamma rays are more energetic than the ultraviolet light that is at the high end of the spectrum of the sun, more energetic than the X-rays that we use to image our bones at the doctor. They're so energetic that they're not being generated by thermal processes in the universe. These photons are strictly non-thermal just because nothing can achieve the temperatures that would be required to create them. The second part of my title was our neighboring galaxy, and by that I mean the Large Magellanic Cloud. The nice thing about the Large Magellanic Cloud is it's close. It has a well-known distance of about 160,000 light years. By Earth scales, this sounds far away, but given the size of the observable universe at about 14 billion light years, this is in our galactic neighborhood. It's also nice that it's face on. So we can imagine maybe some of our studies would be easier done in our own galaxy, the Milky Way. It's closer. But the problem with the Milky Way is it's viewed edge on. So you can imagine kind of like trying to pick out the best slice of pizza by looking at the pizza edge on. It's hard to do. You can't see which slice has the most toppings. You can't see which is the biggest slice. Well, with the Large Magellanic Cloud, we have our pizza face on. We can see all the pepperoni and cheese quite easily. And important for my study is that this galaxy has been very significantly detected by the Fermi Gamma Ray Space Telescope. Okay, so what's our picture? We said that gamma rays are not being generated by thermal processes, so how do we think they get there? Well, the story begins with star formation. Gas that's available in the Large Magellanic Cloud is through some processes, mainly gravitation, able to collapse to form stars. The most massive of these stars that we create are going to burn hottest, live fastest, and die youngest. And when they die, they're going to cause explosions known as supernovae. These supernovae are going to shock the surrounding interstellar material. And across these shock fronts, we're going to accelerate charged particles known as cosmic rays. These cosmic rays consist mostly of electrons and protons, but also include heavier atomic nuclei as well, and there's positron component. Now we have our cosmic rays. If we consider the protons, those can now collide with thermal ambient protons in the interstellar medium. And when these collisions happen, one product is a neutral pion. These neutral pions have very short lifetime, and they'll decay to the gamma rays that we've seen in the picture shown on the first slide. So this model has been around for something like 70 years, but it's only now that with the great data from the Fermi telescope that we're able to start testing it. And one way to test it is what I'm doing, is by comparing the what we think are the relevant components, galactic components of the Large Magellanic Cloud to the gamma ray emission. So on the far left here, we have a map of the thermal ambient protons, ionized hydrogen. These are the colliders for our cosmic ray protons. And on the right, we have a couple of maps of star formation rate. We said star formation was the starting place for how to create cosmic rays. Now, using least squares likelihood fitting, we fit a combination of these maps to the data, the gamma ray data below on the left, and our best fit results in a residual that doesn't really seem to indicate that there were any high counts there at all. So we think we're doing well with this fit, and we're supporting the picture that I painted in the previous slide. Okay, so now we have an idea based on observations of how we think these gamma or cosmic rays are being accelerated through supernovae. So what simulations can do is help us understand how these charged particles move around the galaxy once they have been accelerated. So to do our work, we're going to use the Adaptive Mesh Magnetohydrodynamics code, FLASH. It's an open source code widely used in the astronomy field. FLASH also has a particle mesh gravity solver, which we heard about a little bit in an earlier talk. And recently, cosmic ray propagation module has been added to the code. Cosmic rays are treated as a fluid on the numerical grid, and this fluid undergoes, or the equation of motion depends on advection, diffusion, sourcing, and energy losses. Okay, so as I said, we want to better describe the motions of cosmic rays after they've been accelerated. To do this, we really want to make a realistic simulation of the Large Magellanic Cloud. And our simulations are going to depend on quite a bit of physics, not least of which includes magnetic field topology. We're talking about charged particles, so their motions will care about the presence of magnetic fields. We need to know about the density, the presence of the thermal interstellar medium, because those are the particles that, when we collide our protons with, are going to generate the gamma rays. Star formation is important for sourcing of our cosmic rays. We'll wish to model energy losses, and also important is properly modeling the gravitational potential. So on the right is a simulation that we've done of the LMC's potential. The way it's initialized is that this disk shown will maintain its profile in isolation, but we've introduced tidal forces from the Large Magellanic Cloud's neighbors, and we'll see this has a profound effect on the morphology. And again, we're looking at the disk of the Large Magellanic Cloud face on here. So we see some tidal stretching and development of spiral arm structure. So I'll end with some future work that we wish to perform. We'd like to continue adding physics to our Large Magellanic Cloud simulation, and we'll constrain the numerical model for cosmic rays by comparing the our simulated data with the gamma ray observations. Additionally, we'd like to investigate how we might enhance our calculations by accelerating the flash code using the GPU architecture Currently, flash is CPU only. And additionally, we'd like to perform a study of an additional nearby galaxy called the Small Magellanic Cloud to see whether our gamma ray model holds in a pretty different environment. So I'll end with that, and thank you very much.
Well, thank you. We have time for a couple of questions. I'll start. How large are those data sets, the experimental one? Because your image looks like 200 by 300 pixels, but it's probably more than that.
So the image I showed is about 200 by 200 pixels. It's an all-sky survey though, so we haven't been trained on just the LMC for the full time. And the resolution of gamma ray astronomy is also pretty low as well. So actually our pixel sampling is beyond the true resolution of the telescope. Yeah.
Other questions? Well, if not, let's thank all the speakers today.